and she's going to speak on Gauss-Lucas theorem in polynomial dynamics. And she's from Mathematical Reviews, yes?
That's right.
Okay.
Mathematical Reviews, American Mathematical Society. We are obliged to say, stress the parent organization wherever we go. Anyhow, thank you very much for the introduction, for the invitation, and well, I guess for the privilege of starting the holomorphic dynamics for this week, in this holomorphic dynamics semester. So that would be polynomial dynamics, just to get you started. For those who come from different backgrounds, I remind some, for those who work in holomorphic dynamics, just to focus your attention of what kind of holomorphic dynamics is going to happen. So there is a rational function of the degree d greater than 1. You can think of the d as a topological degree or as a maximum of degree of numerator and denominator. We treat it as a holomorphic map of the Riemann sphere, which is a natural thing to do. And then in dynamics, two sets are defined. Fatu set is the maximum open subset of the sphere on which the sequence of iterates, that's my notation for the iterate, is equicontinuous or normal, if you prefer. And Julia set is its complement. Julia set is closed and non-empty. Rational map, well, it's infinite anyway. And both are totally invariant under F. So they coincide with their images and preimages.
Sorry, I need to share.
Oh boy.
I apologize for the disruption. We forgot to share the slides.
Oh, great.
No,
So just
sorry.
Just to focus your attention on the what kind of dynamics is going to happen.
Well,
Screen sharing. Control L. Control L.
Okay. Yeah.
Okay. And now I don't know how to move the slides anymore.
Philippe,
Okay, now the keyboard did magic, thank you. So, as I announced, this would be about polynomial dynamics. So we know that infinity is the exceptional point. It's a fixed point, and also the backward orbit coincides with the point. This is the point in Fatu set, and the Julia set of a polynomial always has empty interior. And well, when we write down this asymptotic inequality, that would tell us there is a big disk such that the preimage of the disk is contained in this disk. And whenever we have such a disk and keep iterating backwards, and then well, K naught should be probably 1, but then you take the intersection of those backwards iterations, preimages of the disk, look at an object that is called the field Julia set of a polynomial, which is just a set of points such that the forward orbit is bounded. So this is also a completely invariant set. Moreover, this is the union of the Julia set with bounded components of the Fatu set, and Julia set is the boundary of the field in Julia set. This will all play a role, that's why I'm spending time on that. So the natural question is, do there exist non-trivial closed sets other than Julia set, of course, and whatever we saw before? such that the preimage of the set is contained in the set itself. Well, non-trivial, I mean, don't give me a backward outbit of the point or anything like that. Well, there's a more specific, more interesting question. Let's take a complex polynomial of the degree at least 2. Let's take the convex hull of the Julia set of the polynomial. So, does the preimage of the convex hull lie in the convex hull itself? And this was asked and conjectured to be the case by Per Alexandersson in 2020. And I happen to answer this question positively. So this is what the talk is going to be about. Why is it so? So, there's no holomorphic dynamics talk without the picture of the Julia set. So I borrowed from Alexandersson his example. This is this cubic that you see written down. What's the significance of the colors? The dark blue is the Julia set. The light blue is the convex hull, and the black dots are points in the preimage. Of course, not all of them, because we wouldn't see anything if they did this way, but you can kind of see why the conjecture was formulated, because you see all of them inside the convex hull.
Black or what?
The black dots, these guys.
What are they?
The points of the preimage of the convex hull. Preimages of the light blue guys.
But they're points or they're preimages of the entire set and they.
No. These are just a bunch of points. He takes some point somewhere and plots it here. And well, he cannot plot the whole thing blank because we wouldn't see what's happening.
So this set is going to be completely invariant actually.
No, it cannot be completely invariant. No.
That's why there are no black dots in this.
They are, whatever is colored black lies in the region that is colored light blue. That is the conjecture.
That's why there are regions in the light blue which have no black points.
I think there's a visibility issue that cannot be totally disconnected, right? That's not what the picture is saying, and that's not what is happening. It's just set theoretical thing. So these are not all the points, because otherwise, you would cover the Julia set in black and such, so the picture wouldn't be that instructive, right?
But what I'm asking is that, this picture clearly has these entrances, these things that look like pictures or something. And why do we see that?
It is a degree.
Excuse me?
It's because it's not 1 by 1, it's like D to 1. So the preimage is like.
Yeah, the map is not 1-to-1. So, well, it's a degree D map. So, yes.
Because what I'm realizing is just that the preimage of the convex hull is strictly inside, right?
Yes. That's what this picture is trying to convey. Yeah, we don't see the whole preimage. That's what I am saying. We see some points here, but if we wanted to see everything, then we have to paint Julia set black and.
No, but I think, and it's also my question. So
Yeah.
I think Anna's question was whether, based on that picture, we're supposed to believe that the preimage is strictly contained. The preimage of the blue thing is strictly a strict subset of itself.
Not necessarily. You might have. You can have this.
So that's what we asked.
That's part of
I think that's the next legitimate question to ask, and the answer is no, because there might be Julia sets that are on the boundary.
We get it.
Something wrong?
No.
Okay. So if you want to, what's up? Well, the relation between convex sets and complex polynomials is given by the Gauss-Lucas theorem. So if you want to prove anything, you are looking for results that can help you. So every convex set in the complex plane containing all zeros of the complex polynomial also contains all the critical points. Well, from now on, we forget the infinity. We are in the complex plane, and critical points are solutions to, zeros of the first order derivative. So that's what they are. And there is an equivalent theorem, more geometrically expressed by William Thurston and published posthumously by his collaborators. Theorem concerns a polynomial degree at least 2. Let's take the convex hull of the critical points now, and then take any closed half plane intersecting this convex hull, and consider P as a map from this closed half plane to the complex plane. Turns out this is a surjection. It's equivalent, not that hard to prove. And then other useful result goes to Hermander. It's stated as an exercise in his book on convexity, but I think he's missing some assumption. So I'll formulate it in the form I'm going to use it. Let P be a complex polynomial and let B be a closed convex subset of C containing all zeros of P prime. Then the set CD of all points such that, well, whose preimages are contained in B is a convex set. I formulated it in terms of zeros of the polynomials because that is also convenient. The proof is not that hard. You define another polynomial. You take two points in this convex set, 2 exponents, and consider one variable polynomial like this. And all zeros of this polynomial lie in B because these 2 points were they in the set that you defined. Well, the convex hull of zeros is also contained in B. B is convex, right? So now you use Gauss-Lucas. So all the zeros of big B prime are contained in B. And what are those? All the zeros of this polynomial, all the zeros of these polynomials, and well, you have multiple zeros. If n1 and n2 are greater than 1, well, you have all the zeros of P prime, all the zeros of such a polynomial. So this combination is in the set CB, and then you use the fact that the set is closed and the rationals are dense, manipulate your exponents. So you get that the convex combination of points is in the set. Done. And now the hyperplane separation theorem, which everybody knows, and this is the version I'll be using, so I took the liberty to state it for you. We have a convex and closed set in a finite dimensional vector space V. So our vector space V will be just R2. So it's a little bit deviation from the complex setting. So let's take a point not in this convex closed set. So then there is an affine half space containing this point which doesn't intersect our convex set. Or if we prefer the formulation in terms of affine functions, that's how it works. That is actually earlier than Han Banach. That is by Minkowski. And I don't think it's so, let's say, set theoretically heavy as Han Banach is.
No, Han Banach is an infinite dimension.
Yes, but this particular version is Minkowski. So that's also dynamical Gauss-Lucas. So let's take a polynomial of degree at least 2, and then all zeros of the derivative belong to the convex hull of the Julia set. So this is kind of surprising at the first glance because, well, we all know that the fact whether critical points are or aren't in the Julia set determines the topology, and the behavior can be very, very different for very different polynomials. Then it turns out that wherever the critical points are, they are never that far from the Julia set. So let's do by contradiction. Suppose there is a point, the critical point of the polynomial outside the convex hull of the Julia set. So let's separate it by the closed half plane so that this critical point remains in the half plane and the Julia set remains on the other side. There's no intersection. So by Thurston theorem, we have a surjection in here. We have Julia set on this one side of the hyperplane. So let's take a point. And let's take the preimages. On one hand, Julia set is totally invariant, so the preimages all sit in the Julia set. But then Thurston tells us that this map was surjective, so that some preimage has to hit E, and we get a contradiction. So the main result now follows very quickly. Indeed, we have what we kind of saw in the picture. If we have a polynomial of degree D greater or equal than 2, then the preimage of the convex hull of the Julia set lies in the convex hull itself. So to prove it, let's observe that by this lemma that we just saw, the convex hull of the Julia set is a closed convex set that contains all the critical points. So now Hermander's lemma tells us that this set, now I denote it by P because of the dependence of this set on P. So this set is convex. And well, Julia set, of course, is invariant. If we take a point, then all the preimages lie in the Julia set, as also in the convex hull. So the Julia set lies in this convex hull. But this is convex, so if we form the whole hull will be in there, which is another way of writing down that the preimage of HP lies in HP, if you look at the definition of the set CP. So this is the main result. So I still have a couple of minutes, and I promise to discuss some special cases, the cases where the equality is achieved. Well, first, the special case. All this machinery wouldn't be, let's say, needed. All this connection with Gauss-Lucas and Hermander and Thurston would be totally swept under the carpet if we just looked at quadratic polynomial. Maybe Gauss-Lucas, maybe Thurston, but we would have to establish the dynamical lemma. If you take a quadratic, there's only one finite critical point, this is 0. That's the center of symmetry of the Julia set. So there's a convex combination of 2 points. So critical points, the critical point is in the convex hull of the Julia set. But that's a special case. So what are the cases where equality is achieved? This is if and only if the Julia set is either a line interval, line segment, because for the polynomial case, this has to be compact, or a circle. So up to Möbius conjugacy, we are dealing here with, well, in the case of interval, we are dealing with the Chebyshev polynomial, the minus Chebyshev polynomial, the ones that you know from, let's say, approximation theory or potential theory. There is the three-term recurrence formula, which I didn't write down, but these are well known. And in case of the unit circle, these are the just powers of the variable z multiplied by a unimodular complex number. So here it gets a little bit tricky. This is a notion of holomorphically convex hull. In the plane, I guess I could just talk about polynomially convex hull because this turns out to be the same. But anyhow, I started on the high note. Let me continue. Let omega be an open set in C, and let A of omega denote the class of all holomorphic functions. And now let's take Z, just any compact subset of this open omega. Omega doesn't have to be bounded or anything. So what's the holomorphically convex hull Z hat of Z in omega? This is relative to omega, so we have to bear this in mind. So these are all points such that the modulus of f of Z is less or equal than the uniform norm of f of the set Z for every f holomorphic in omega. So if you, instead of all holomorphic functions, take the family of all complex polynomials, that you get a polynomially convex hull, but then in the plane you will get the same object. And topologically, when you look at that, but also there's a planar thing in CN, tricky things can happen, but we are in the plane, so we don't have to worry. How do you get the holomorphically convex hull? That's the union of Z and the connected components of the complement, which are relatively compact in the set of omega. So if you have a, let's say, compact in the plane, the way to obtain the holomorphically convex hull is just to paint the holes the same color your set was painted. And forget the infinite component. So it's not hard to prove that this hull is contained in the convex hull. You can think of the fine maps here. I'll not go into details on that. So for the polynomial, the convex hull of the Julia set would be just the Julia set that we saw. Easy done. So auxiliary results are that, well, since this is easy, and I told you on the previous slide, this is the holomorphically convex hull of the Julia set. Holomorphically convex hull lies in the convex hull in the usual sense.
So didn't you call the holomorphically convex cone something?
No, cone is the convex hull that we all know, you know, they take 2 points and the segment and such. It's this kind of convexity, you know, with respect to affine maps, you can set up the definition of convexity in this way using the affine maps here. So, so that's why this object also got to the convex in its name, but that can be kind of misleading if you deal with both of them at the same time. So it's good that you asked. So we have the convex hull that we all know and use very often, but this is a probably new object for many of you. But these are well-studied things in complex analysis. So because in several variables, interesting things happen. In the one complex variable, you just paint the holes. So, but that's a good thing for us here in the complex plane. So, turns out that if the preimage of the convex hull of the Julia set is the same as the convex hull, then the convex hull itself lies in the field in Julia set. That's not hard to prove. You take intersection and such, and you observe. So in particular, the Julia set is the boundary of the convex hull, of its own convex hull. So that's already something that tells us a lot. I should be wrapping up.
No, you still have time to.
Okay. The boundary of a convex set with a non-empty interior in R2 is a Jordan curve. That's not so trivial. These are very non-trivial things that we have on this blackboard. Maybe, furthermore, the Hausdorff dimension of this Jordan curve is one of the boundary of a convex set. So that's a geometric measure theory thing. It's not trivial, so I cannot give you a proof, even if I wanted this remaining time.
It's rectifiable.
Rectifiable is the name, yes. That's right. That's right. Now, this is not how I did it in the publication, but since I am here, I thought I should mention those results that can also lead to the conclusion. Now, Felix Przetycki proved in 1985, or maybe earlier, but that's a publication in Invenciones, the Hausdorff dimension of harmonic measure of the boundary of attractive basin at infinity for a polynomial is 1. You prove more than that, but that's the conclusion I need here.
The same year Makarov proved that you don't need dynamics.
Sure, but then there was a result. I'm not going to define these objects. That's way too complicated and way too long for whatever remaining time we have. Anders Dunik, 5 years later, proved that Hausdorff dimension of the Julia set of a rational function is greater than Hausdorff dimension of the harmonic measure on the boundary of the attracting basin infinity, unless F is critically finite with parabolic orbifolds. And those maps are classified up to conjugacy, and that's the last, let's say, point here on this slide. Again, I'm not gonna define what the parabolic orbifold is, but those maps that are exceptional in point 3 are which the sets that are not the whole sphere are exactly positive and negative powers or plus minus Chebyshev polynomials. So exactly the ones that we expected. So again, to recapitulate, the boundary is the boundary of the convex hull of the Julia set is the Julia set if you have equality. This is a Jordan curve of finite length. So the map it comes from has to be up to a Möbius conjugacy, either the positive power of the variable or plus minus Chebyshev polynomial. These are all the possibilities, because for the polynomials we don't get Julia set, which is the whole sphere. So this is the conclusion. If I still have a little bit time, I can tell you what I don't know about rational maps. But if you have questions on the polynomial cases, maybe it's a good place to, let's say, to ask them. So that's not how I did it originally, but these are deep results worth, let's say, propagating. So I put them in here. I did it actually very simply minded way. Maybe not. Let me tell you what I don't know about the rational maps. Well, if let's say, for the sake of not having to deal with circles, but with straight lines, let's assume that infinity is the Fatou set, so the Julia set is bounded, contained in the complex plane. So the problem to ask whether the preimage of the convex hull of the Julia set makes sense for rational maps. But then you can observe very different behavior. I don't know the answer, but you can probably come up with this very simple-minded example, 1 over z squared. So the Julia set is a unit circle, the convex hull is the unit disk, but then if you keep iterating backwards, you get outside and inside and outside and inside. So not quite what is observed in the polynomial case. So the all backward images are not contained in the convex hull of the Julia set, but even backward preimages are. Now, this is more complicated. And then, well, I borrowed examples from people who studied them for totally different purposes. So I didn't invent anything, but I looked at them from the perspective of convex hulls. So I'm not responsible for, fine-tuning of the parameters or drawing any pictures. So this is more sophisticated of the example when the preimage of the convex hull of the Julia set is not contained in the Julia set, and no iterate can help you. No matter what iterate you take, you will always have something outside. So this is complicated cubic with the parameter rho depending on epsilon in such a way, and epsilon between 0 and 1. That is borrowed from the paper by Daniel Luke, who also drew the picture that I'm going to show. This is the Julia set, not very fine grained, but he studied chiapistic upper Julia sets. So that's what he obtained, and that's how he obtained those by studying this.
In general, if the function is not polynomial,
Yeah.
then there must be poles.
Sure.
So they are not in Julia set, but convex hollow Julia set.
Might be, yes. That's the. Yes. How hard to come up with, let's say, a reasonable condition for this. And indeed, the pole is the obstruction in here, because 0 is a super attracting fixed point. The preimages of zeros are 0 at infinity. It's a pole, let me just remind you. No, it's not a pole. 0 is not a pole. Yeah, but it's the preimage is at infinity. We are talking about preimages, not images. So let's talk about immediate attracting basin of 0. That's simply connected, bounded by a simple closed curve. But we have a neighborhood of infinity which is mapped onto this neighborhood of 0, this immediate attracting basin. But when you take the preimage, it will have two components. One is this attracting basin of 0, and the other component is the neighborhood of infinity. Then you take your convex hulls, but it doesn't help. So this is this one, and it has, for a while I thought it might have to do with the fact that infinity is an attracting basin. I was trying to express convexity in terms of circles rather than straight lines, and see this behavior that we observe for this big disk for the polynomial. No such luck, and this is from Bearden's book showing an example of the map which has no attracting cycles or super attracting of any period. There is, the Julia set is the unit circle. One is a parabolic fixed point, so it's like you have two petals in the unit disk and the complement of the unit disk. And this is the parabolic fixed point. So that's the dynamics, briefly speaking, over here. Oops, not yet. But this parabolic point happens to be the Julia set, so it's not. Is it parabolic? Yeah, must be parabolic. But the point is that one is in the Julia set. It's not attracting or super attracting because these guys would be in the Fatou set. He even didn't state what the modulus is. But then this is a well-behaved convex hull because it's a unit disk and the preimage coincides with the unit disk. So this has nothing to do with the attracting behavior of infinity and the disk drawn up. So this is not the way to go. And now I can wrap it up. Thank you for your attention.
So convex holes are associated to the Euclidean metric
Yes.
and the planes. But so is there anything very intrinsic about the Euclidean metric associated to this discussion? I mean, we could maybe talk about hyperbolic metric.
The Thurston theorem that made an appearance here was, let's say, a prelude to another theorem, which is stronger than Gauss-Lucas in the same paper, in which he discussed the behavior of the metric. Here is your polynomial in the neighborhood of a critical point. So there was a non-Euclidean metric, and this theorem had to do with, let's say, geodesics. If I remember correctly, I might not on top of my mind, but it's in the paper of Thurston that was published posthumously by other people from his notes. So if I remember correctly, there was a convex hull of the critical points of a polynomial, a line going through one of those in such a way that the convex hull stays on one side, and at this critical point that lies on the lane, it turns out you can get an open set of directions of geodesics in this metric, such that the closure of this open set is mapped surjectively onto the plane. So that's how Thurston got involved into Gauss-Lucas, because that was, I think, either a stepping stone or something along those lines, and it's in these papers from 2015 that Sherita, Leighton, and two other mathematicians published from his notes. So there was a non-Euclidean metric, this thing around the critical point, but other than that, well, the whole thing is not very odd, so I don't know how to deal with that.
Well, I guess there are no other questions, so let's thank our speaker again.